with its vibrant stripes and swirling storms. Jupiter is a true marvel of the cosmos, but it's not just its beauty that has captivated us. Jupiter has also revealed many secrets about the universe we live in. Over the years, a dozen space missions have been launched to explore Jupiter and unlock its mysteries. These missions have revealed a wealth of information about the planet's composition, atmosphere, and magnetic field, and have led to some incredible discoveries. So are you ready to explore one of the most fascinating planets in our solar system? Get ready for an out-of-this-world adventure as we delve into the incredible discoveries of Jupiter. Join us as we journey through time and space to discover the fascinating history of Jupiter, from its early formation to the latest groundbreaking discoveries. Discover the latest findings from NASA's Juno spacecraft, which has been orbiting Jupiter since 2016 and providing us with unprecedented views of the planet's atmosphere and magnetic field. So sit back, relax, and get ready to be blown away by the incredible discoveries of Jupiter. This is a journey you won't want to miss. In June of 2021, the Juno spacecraft made history by becoming the first spacecraft to hear the sound of Jupiter's moon, Ganymede. The discovery was made possible by the spacecraft's radio wave instrument, which detected radio waves generated by charged particles in Ganymede's magnetic field. Ganymede is the largest moon in our solar system and is larger than the planet Mercury. It has a magnetic field that interacts with Jupiter's magnetic field, creating a unique set of charged particles that generate radio waves. These radio waves can be detected by spacecraft, providing scientists with valuable information about the moon's magnetic field and atmosphere. Juno's radio wave instrument, called the WAVES instrument, was designed to study Jupiter's magnetic field and auroras. However, during a flyby of Ganymede in June of 2021, the instrument detected a unique set of radio waves that were not expected. Upon closer analysis, scientists realized that the radio waves were generated by Ganymede's magnetic field and atmosphere. The WAVES instrument detected the radio waves in the form of Whistler mode waves, which are a type of electromagnetic wave that travels along the magnetic field lines of a planet or moon. Whistler mode waves are commonly detected on Earth and other planets, but this was the first time they had been detected on a moon. The discovery of the radio waves has provided scientists with valuable information about Ganymede's magnetic field and atmosphere. By studying the characteristics of the radio waves, scientists can learn about the density, temperature, and composition of the charged particles in the moon's environment. In addition to providing valuable scientific data, the discovery of the radio waves has also captured the imagination of the public. The sound of the radio waves was converted into an audio file, allowing people to hear what Ganymede sounds like. The sound is a unique set of whistles and pops that provide a fascinating glimpse into the moon's magnetic field and atmosphere. The moons of Jupiter. One of the most interesting aspects of Jupiter is its numerous moons. Jupiter has a total of 92 known moons, making it the planet with the most moons in our solar system. Among these moons are some of the largest and most interesting in our solar system. Europa. One of Jupiter's most intriguing moons is Europa. Discovered by Galileo Galilei in 1610, Europa is the sixth largest moon in our solar system. Europa is an exciting target for astrobiology, as scientists believe that it could potentially harbor life. One of the most significant discoveries made on Europa was the presence of a global subsurface ocean beneath its icy surface. This discovery was made through observations of the moon's gravitational field and has been confirmed by multiple spacecraft flybys. Scientists believe that this ocean contains more than twice as much water as all the oceans on Earth combined, making it a potentially habitable environment for life. Another important discovery was the presence of geysers erupting from Europa's surface. The Hubble Space Telescope first detected evidence of these plumes in 2012, and subsequent observations by the Galileo spacecraft and the Hubble have confirmed their existence. These geysers suggest that the ocean beneath Europa's surface is interacting with its icy crust, which could be a source of nutrients for potential life forms. Europa's icy surface has also been the focus of intense study. Images from the Galileo spacecraft have revealed a complex network of cracks and ridges on the Moon's surface, which suggests that the icy crust is in a constant state of flux. In 2018, scientists discovered evidence of large chaos terrains, which are areas where the icy crust appear to have been disrupted and rearranged. These features suggest that the subsurface ocean is actively interacting with the Moon's crust, which could have important implications for the potential habitability of Europa. In addition to these discoveries, scientists have also studied the chemical composition of Europa's surface. Spectroscopic observations have revealed the presence of sodium chloride in the Moon's surface, which is consistent with the hypothesis that Europa's ocean is in contact with its rocky mantle. This raises the possibility that the ocean could be chemically active, which could provide further support for the existence of life on the Moon. Ganymede. Another of Jupiter's fascinating moons is Ganymede, the largest moon in the solar system. Discovered by Galileo in 1610, Ganymede is unique among moons in our solar system because it has its own magnetic field. In 1996, NASA's Galileo mission discovered that Ganymede had a tenuous atmosphere made up of oxygen. This discovery was surprising, as Ganymede was not expected to have an atmosphere due to its low gravity. The discovery of an atmosphere on Ganymede raised new questions about the Moon's history and composition. One of the most significant discoveries made on Ganymede was the presence of a subsurface ocean beneath its icy surface. This discovery was made by the Galileo spacecraft in the late 1990s through observations of the Moon's magnetic field. The presence of an ocean beneath the icy crust is significant because it suggests that Ganymede may have the conditions necessary for life to exist. Scientists have also studied the chemical composition of Ganymede's surface. Spectroscopic observations have revealed the presence of water ice, carbon dioxide, and other compounds on the Moon's surface. The presence of these compounds suggests that Ganymede has a complex geologic history and may have formed in a different part of the solar system than the other icy moons. Another important discovery was the presence of a magnetic field around Ganymede. This magnetic field is thought to be generated by the Moon's liquid iron core, which is unique among the icy moons of the outer solar system. The magnetic field is also significant because it interacts with Jupiter's magnetosphere, creating a complex and dynamic environment around the Moon. Ganymede's surface has also been the focus of intense study. Images from the Galileo spacecraft and the Hubble Space Telescope have revealed a complex network of grooves, ridges, and craters on the Moon's surface, suggesting that it has a dynamic and active geologic history. In 2021, the Juno spacecraft conducted a flyby of Ganymede, providing new high-resolution images of the Moon's surface that will help scientists better understand its geology and composition. Io. Io is another of Jupiter's fascinating moons. Discovered by Galileo in 1610, Io is the fourth largest moon in the solar system and is known for its intense volcanic activity. Io's volcanoes are some of the most active in the solar system, with eruptions spewing out lava and other material. In 1979, NASA's Voyager 1 spacecraft made a close flyby of Io, providing scientists with their first close-up look at the Moon. The mission revealed a surface covered in volcanic activity, with plumes of material erupting from the Moon's surface. Subsequent missions have revealed the presence of over 400 active volcanoes on the Moon's surface. These volcanoes erupt sulfur, sulfur dioxide, and other compounds, creating a colorful and dynamic landscape. Another important discovery was the presence of a thin atmosphere around Io. This atmosphere is composed mainly of sulfur dioxide and is thought to be created by the volcanic activity on the Moon's surface. The atmosphere also interacts with Jupiter's magnetosphere, creating intense radiation belts around the Moon that pose a potential hazard for spacecraft and future human exploration. Io's surface has also been the focus of intense study. Images from the Voyager and Galileo spacecraft have revealed a complex network of mountains, valleys, and plains on the Moon's surface. These features are thought to be created by the intense volcanic activity and tectonic forces on Io's surface, making it a unique laboratory for studying geologic processes. In addition to these discoveries, scientists have also studied the chemical composition of Io's surface. Spectroscopic observations have revealed the presence of sulfur, sulfur dioxide, and other compounds on the Moon's surface, providing important insights in the geological processes at work on the Moon. In addition to these moons, Jupiter has many other interesting satellites, each with its own unique features and characteristics. Callisto, for example, is the second largest moon in the solar system and has a heavily cratered surface. Amalthea is a small, irregularly shaped moon that orbits close to Jupiter and is believed to be a captured asteroid. Jupiter's weather patterns. Jupiter's weather patterns are another area of interest for scientists studying this gas giant. Jupiter has some of the most extreme weather patterns in our solar system, with massive storms and hurricanes raging across its surface. One of the most well-known weather patterns on Jupiter is the Great Red Spot. This massive storm has been raging on Jupiter for hundreds of years and is larger than the size of the Earth. The Great Red Spot is thought to be a high-pressure system with winds that can reach speeds of over 400 miles per hour. In recent years, scientists have been monitoring the Great Red Spot closely, hoping to learn more about this massive storm. In 2019, data from NASA's Juno spacecraft revealed new insights into the storm, suggesting that it extends deeper into Jupiter's atmosphere than previously thought. The Juno mission also provided scientists with new data on the chemistry and composition of the Great Red Spot, offering further insights into the storm's behavior and potential impact on Jupiter's atmosphere. Another striking weather pattern on Jupiter is the planet's intense lightning storms. Jupiter is known for its frequent lightning activity, with bolts of lightning occurring on the planet at a rate of up to 4 times that of Earth. Scientists have been studying Jupiter's lightning storms for decades, hoping to learn more about their behavior and potential impact on the planet's atmosphere. In 1979, NASA's Voyager 1 spacecraft made a close flyby of Jupiter, providing scientists with their first up-close look at the planet's lightning activity. The mission revealed that Jupiter's lightning storms are much more intense than those on Earth, with bolts that are hundreds of times more powerful than those on our own planet. The atmosphere of Jupiter is composed mostly of hydrogen and helium, with small amounts of other gases like methane, ammonia, and water vapor. The atmospheric pressure on Jupiter is also much higher than on Earth, with a pressure at the surface that is 100 times greater than on our planet. In recent years, scientists have continued to study Jupiter's lightning activity, using data from spacecraft such as NASA's Juno and the European Space Agency's Jupiter Icy Moons Explorer (JUICE) mission. These missions have provided new insights into the behavior of Jupiter's lightning storms, as well as their potential impact on the planet's atmosphere. The intense atmospheric conditions on Jupiter create strong electric fields that can generate lightning strikes thousands of times more powerful than those on Earth. The electric fields on Jupiter are generated by a combination of factors, including the planet's rapid rotation, which creates strong winds and turbulence in the atmosphere, and the interaction between the magnetic field of Jupiter and the solar wind. Most of the lightning on Jupiter is concentrated in its polar regions, where the magnetic field is the strongest. The lightning on Jupiter is also notable for its frequency, which is much higher than the frequency of lightning on Earth. On Earth, lightning occurs at a frequency of about 40 to 50 times per second, while on Jupiter it occurs at a frequency of several hundred times per second. One interesting feature of Jupiter's lightning is that it appears to be associated with storms in the planet's atmosphere. Some of these storms can be quite large, with cloud structures that are thousands of kilometers in size. The lightning associated with these storms can be observed using telescopes that detect radio signals, which are generated by the electrical discharges. Jupiter's atmosphere is also known for its colorful cloud bands. These bands are made up of different types of gases and are responsible for Jupiter's distinctive appearance. The cloud bands are formed by powerful jet streams that circulate around the planet, with the different colors and patterns caused by variations in the composition and temperature of the gases in the atmosphere. The reddish-brown color of the lower clouds is caused by the presence of complex organic molecules, which are formed when sunlight reacts with methane and other hydrocarbons in the atmosphere. The bluish-white color of the higher clouds is caused by the presence of ammonia ice crystals, which reflect sunlight in the blue part of the spectrum. In recent years, scientists have been studying Jupiter's cloud bands in greater detail, using data from missions such as NASA's Juno and the Hubble Space Telescope. These missions have provided new insights into the behavior of the cloud bands, as well as their potential impact on Jupiter's atmosphere and weather patterns. Jupiter's magnetosphere. In recent years, NASA's Juno spacecraft has provided us with an unprecedented look at Jupiter's magnetosphere, a massive and dynamic region of space surrounding the gas giant. This has allowed scientists to make several significant discoveries about this fascinating environment and how it affects the planet. Have you ever heard that the Great Red Spot had a sibling called the magnetic Great Blue Spot? Similar to Jupiter's famous Great Red Spot, which is a giant storm larger than the size of Earth, the magnetic Great Blue Spot is a massive structure within Jupiter's magnetic field. Unlike the Great Red Spot, which is a visible storm on the planet's surface, the magnetic Great Blue Spot is invisible to the naked eye and can only be detected by spacecraft instruments. The magnetic Great Blue Spot was discovered using Juno's magnetometer instrument, which measures the strength and direction of magnetic fields around Jupiter. The instrument detected a unique pattern of magnetic field lines in the southern hemisphere of Jupiter, similar to the pattern created by the Great Red Spot. Upon closer analysis, scientists realized that the magnetic field lines were caused by a massive structure within Jupiter's magnetic field. The structure is thought to be a massive cyclone similar to the Great Red Spot, but located within Jupiter's magnetic field instead of its atmosphere. The discovery of the magnetic Great Blue Spot is significant because it provides new insights into the complex magnetic field surrounding Jupiter. The structure is thought to be created by the interaction between the planet's strong magnetic field and the electrically charged particles in its atmosphere. The magnetic Great Blue Spot is also significant because it may help scientists understand the origins of Jupiter's powerful auroras. Auroras are caused by charged particles from the solar wind interacting with the planet's magnetic field. Jupiter's auroras are some of the most powerful in the solar system, and understanding the structure of the planet's magnetic field is crucial for understanding how they are created. One of the most exciting findings was the discovery of Whistler waves within Jupiter's magnetosphere, like the one Ganymede gave us a glimpse of. These are electromagnetic waves that travel along the magnetic field lines, causing a distinct whistling sound when they are converted into audio frequencies. Scientists believe that these waves play a significant role in the acceleration of particles within Jupiter's magnetosphere, which contributes to the intense radiation that characterizes this region of space. Juno has also revealed that Jupiter's magnetosphere is significantly more complex than previously thought. The spacecraft detected unexpected pockets of magnetic field activity, as well as unusual structures known as plasmoids, which are large masses of plasma that can break off from the main body of the magnetosphere and travel along the magnetic field lines. Perhaps most excitingly, Juno has provided us with the first direct measurements of Jupiter's polar magnetosphere. This has allowed scientists to better understand how the planet's magnetic field behaves at its poles, which is essential for understanding the planet's overall magnetic field structure. Jupiter is known for having one of the strongest magnetic fields in our solar system, with a magnetic field that is about 20,000 times stronger than Earth's. The magnetic field is so strong that it creates a huge magnetosphere around the planet that extends over 5 million kilometers into space. If Jupiter's magnetosphere emitted visible light, it would appear to be 2 to 3 times the size of the Sun or Moon to observers on Earth, making it the largest entity in the solar system. But how did Jupiter form such a powerful magnetic field? To understand how Jupiter formed its magnetic field, we need to take a closer look at the planet's interior. Jupiter is a gas giant made mostly of hydrogen and helium, with a small rocky core at its center. The pressure and temperature from the planet's interior are so extreme that the hydrogen gas is squeezed into a metallic form, which conducts electricity. The metallic hydrogen in Jupiter's interior acts like a liquid metal, and as the planet rotates, it creates a dynamo effect that generates a magnetic field. This is similar to how Earth's magnetic field is generated by the motion of molten iron in its core. However, Jupiter's magnetic field is much stronger than Earth's because of the planet's size and rapid rotation. Jupiter's rapid rotation is one of the key factors that contribute to the strength of its magnetic field. The planet rotates once every 9 hours and 56 minutes, which is much faster than any other planet in our solar system. This rapid rotation causes the metallic hydrogen in Jupiter's interior to flow more rapidly, which generates stronger electric currents and a more powerful magnetic field. Another important factor is the size of Jupiter. As the largest planet in our solar system, Jupiter has a massive interior with a core that is likely very dense and rich in metallic hydrogen. This provides the ideal conditions for a dynamo to form, with ample electrically conducting material available to generate the magnetic field. But Jupiter's magnetic field is not just influenced by its own internal dynamo. The planet's many moons also play a role in shaping its magnetic field. As these moons orbit around Jupiter, they interact with the planet's magnetic field, creating fascinating phenomena such as auroras and plasma waves. In addition to its own magnetic field, Jupiter's magnetosphere also interacts with the solar wind, which is a stream of charged particles emitted by the Sun. This interaction creates a shock wave that protects the planets and its moons from the damaging effects of the solar wind. The magnetic field is so powerful that it poses significant challenges for space missions that venture near the planet. The intense radiation produced by Jupiter's magnetic field can damage spacecraft and their instruments, making it essential to protect them with radiation shielding. Radiation shielding is a crucial component of spacecraft design, and it involves the use of materials that can absorb and deflect radiation. These materials can be in the form of thick layers of metal, ceramic composites, or other materials that have high radiation resistance. For example, the Juno spacecraft that is currently orbiting Jupiter has a radiation shield made of titanium that protects its sensitive instruments from the intense radiation around the planet. In addition to radiation shielding, some spacecraft use Faraday cages to protect sensitive electronic equipment from the intense magnetic fields around Jupiter. A Faraday cage is a conductive enclosure that can protect electronic devices from electromagnetic interference. It works by creating a conductive shield around the equipment, which prevents electromagnetic waves from entering or leaving the enclosure. Careful trajectory planning is also crucial for spacecraft to survive Jupiter's magnetic field. By carefully calculating their path and timing, spacecraft can avoid the most intense regions of the magnetic field and minimize their exposure to radiation and other hazards. This involves using gravitational assists from other planets to adjust the spacecraft's trajectory and increase its speed, as well as executing engine burns to fine-tune the trajectory. To ensure that critical systems on the spacecraft remain operational, redundant systems can be used. If one system fails due to radiation or other factors, backup systems can take over to ensure the spacecraft remains functional. This can include multiple computers, power supplies, and other essential systems. Overall, these discoveries have provided us with a wealth of new information about Jupiter's magnetosphere and its impact on the planet. They are crucial for furthering our understanding of this fascinating environment and its role in shaping the gas giant. With the continued exploration of Jupiter by spacecraft like Juno, there is no doubt that we will continue to uncover new and exciting discoveries about this enigmatic world. The Juno Mission. In 2011, NASA launched the Juno Mission to study Jupiter. Juno arrived at Jupiter in 2016 and has been studying the gas giant ever since. The Juno mission has made many significant discoveries about Jupiter. First, that Jupiter's core is less dense and more spread out than previously thought. One of Juno's key instruments is its gravity science experiment, which uses the spacecraft's precise tracking data to measure variations in Jupiter's gravitational field. By analyzing these variations, scientists can infer the density and distribution of mass within the planet's interior. In 2020, scientists from NASA and other institutions published a study in the journal Nature, revealing the surprising discovery that Jupiter's core is less dense and more spread out than previously thought. The study found that Jupiter's core is not a compact, solid mass as previously assumed, but rather a diffuse, diluted mixture of rocks, ice, and hydrogen and helium gas. The researchers made this discovery by analyzing data from Juno's gravity science experiment and comparing it to computer models of Jupiter's interior. The data showed that the density of Jupiter's core was lower than expected, suggesting that it was more spread out and less compact than previously thought. The discovery of Jupiter's diffuse core has important implications for our understanding of the planet's formation and evolution. It suggests that Jupiter's core did not form through the rapid accumulation of solid material as previously thought, but rather through a slower process of gravitational collapse and mixing of material. The process of Jupiter's formation began with the collapse of a cloud of gas and dust. As the cloud collapsed under its own gravity, it began to spin faster and flatten into a disk. The central region of the disk eventually became dense enough to form the core of the planet, while the outer regions continued to accumulate gas and dust. Jupiter's slow process of gravitational collapse and mixing of material can be attributed to its large size and the low density of the gas and dust in its protoplanetary disk. As the disk cooled and the gas and dust began to settle, the slower-moving particles were able to accumulate around the growing planet. This slow accumulation of material allowed Jupiter to grow larger and more massive over time. Another factor that contributed to Jupiter's slow gravitational collapse was the fact that it formed further away from the Sun than the terrestrial planets. This meant that there was less heat and radiation available to drive the gravitational collapse process, resulting in a slower and more gradual accumulation of material. As Jupiter continued to grow, its gravitational pull became stronger, and it began to attract gas from the outer regions of the protoplanetary disk. This gas was mostly hydrogen and helium, the two most abundant elements in the universe. The gas was pulled towards the planet by its strong gravitational field, and as it fell towards Jupiter, it released gravitational potential energy, which caused it to heat up and compress. The process of gas falling towards Jupiter and heating up is thought to be responsible for the mixing of material in the planet's atmosphere. The heated gas rises to the top of the atmosphere, where it cools and sinks back down, creating circulation patterns that mix the material throughout the planet's atmosphere. Second, Jupiter's magnetic field is even stronger than previously thought. Juno's magnetometer, a crucial instrument, gauges the intensity and orientation of Jupiter's magnetic field. With this information, researchers can deduce the planet's internal makeup and movement patterns, as well as its interactions with the adjacent space. A study published in the journal Nature Astronomy in 2021 by NASA scientists and other institutions revealed a remarkable finding. Jupiter's magnetic field is much more robust than previously believed. According to the research, Jupiter's magnetic field is almost 20,000 times more potent than Earth's magnetic field at the equator and up to 40,000 times stronger at the poles. An analysis of Juno's magnetometer data in comparison to previous measurements taken by the Pioneer and Voyager spacecraft during the 1970s and 80s, the researchers uncovered an unexpected finding. Jupiter's magnetic field, previously believed to be simple and weak, was uncovered to be far more intricate and powerful, with an irregular shape and fluctuating intensity across distinct areas. The revelation of Jupiter's magnified magnetic field carries significant consequences for comprehending the planet's relationships with its moon and the neighboring surroundings. It implies that the magnetic field of Jupiter is even more proficient at capturing charged particles and producing intense radiation belts, which could potentially endanger spacecraft and forthcoming exploration missions involving humans. Third, Jupiter's atmosphere has complex and dynamic weather patterns, with strong jet streams and massive storms. JunoCam, which is among Juno's key instruments, is a visible light camera intended to take high-quality images of Jupiter's atmosphere. With JunoCam's help, scientists have obtained meticulous images of the planet's cloud formations, exposing complex designs and active weather systems. Juno's Jovian Infrared Auroral Mapper, GRAM, is also a crucial tool that examines Jupiter's auroras and atmosphere using infrared imaging. GRAM has unveiled fresh information about the gas makeup of Jupiter's atmosphere, such as the existence of ammonia and other gases. Perhaps the most important instrument on Juno for studying Jupiter's atmosphere is the Juno Microwave Radiometer, JMR. JMR measures the temperature and composition of the planet's atmosphere at various depths, allowing scientists to study the movement of atmospheric gases and the presence of strong jet streams. Through the data collected by Juno's instruments, scientists have discovered that Jupiter's atmosphere has complex and dynamic weather patterns, with strong jet streams and massive storms. They have observed that the planet's atmosphere is organized into a series of east-west and west-east jet streams, some of which reach speeds of up to 620 kilometers per hour. These jet streams are responsible for shaping the planet's cloud formations and weather systems. Juno has also provided scientists with detailed images and data on Jupiter's massive storms, including the famous Great Red Spot, a giant storm larger than the size of Earth that has been raging for at least 350 years. In addition, Juno has observed smaller storms and vortices through Jupiter's atmosphere, providing insight into the mechanisms that drive the planet's weather systems. Finally, that Jupiter's auroras are more intense and complex than previously thought. The ultraviolet imaging spectrograph, UVS, is an essential instrument on Juno that is specifically engineered to examine the auroras on the planet. The year 2017 marked the release of initial findings from Juno's UVS tool, exposing the heightened and elaborate nature of Jupiter's auroras beyond previous assumptions. By gauging the brilliance and spectral features of these auroras, the UVS tool granted researchers a chance to scrutinize their composition and actions. One of the most unexpected revelations provided by the UVS data was the unearthing of impressions located at the foundation of the auroras. These impressions are luminous zones that seem to be linked with the magnetic field lines of the planet, implying that the auroras are molded by the magnetic field in an unconventional manner. The impressions also expose that the auroras are more unpredictable than earlier conjectured, altering rapidly in reaction to the planet's magnetic field. Another surprising discovery from the UVS data was the presence of an inner belt of radiation around Jupiter. This inner belt is made up of high-energy particles that are trapped in the planet's magnetic field and can cause damage to spacecraft and electronics. The discovery of the inner belt has important implications for future missions to Jupiter, as it highlights the need for spacecraft to be designed to withstand the harsh radiation environment. In addition to the Juno spacecraft, other instruments have also contributed to our understanding of Jupiter's auroras. For example, the Hubble Space Telescope has provided stunning images of the planet's auroras, including the discovery of an auroral oval that is much larger than previously thought. The oval is centered on the planet's magnetic pole and is made up of a complex system of bright and dark spots that are constantly changing. The Juno mission captured stunning images of the planet's very faint ring. Jupiter's thin ring is located in the planet's equatorial region and is composed of tiny dust particles. The ring is thought to have formed from material that was ejected from Jupiter's moons, particularly the small inner moons due to impacts from space debris. Over time, this material accumulated to form a thin, dusty ring around the planet. The image captured by Juno shows the ring as a faint, narrow band of light in the planet's equatorial region. The ring is only a few thousand kilometers thick and spans a distance of approximately 12,000 kilometers around the planet. The image also shows that the ring is brighter in certain regions, indicating variations in the size and composition of the dust particles. The discovery of Jupiter's thin ring is significant because it provides new insights into the planet's history and evolution. By studying the composition of the ring particles, scientists can learn more about the origin and evolution of Jupiter's moons, as well as the processes that shaped the planet's early history. The Juno mission has provided scientists with a wealth of new information about Jupiter and has opened up new avenues of research into this gas giant. Jupiter is a fascinating planet that has captured the imagination of scientists and the public alike for centuries. From its numerous moons to its extensive weather patterns and massive magnetosphere, Jupiter has provided us with many opportunities to learn more about our solar system and the universe as a whole. The Juno mission has been particularly significant in advancing our understanding of Jupiter, providing us with new insights into its composition, structure, and behavior. As we continue to study this gas giant, we can expect to learn even more about its many mysteries and complexities. The major discoveries made about Jupiter so far have opened up new frontiers in our understanding of the solar system and the universe as a whole. With its many moons, extreme weather patterns, and massive magnetosphere, Jupiter continues to captivate and inspire us, providing us with new opportunities to explore and discover. Thanks for watching. We hope you enjoyed this video about everything we know about Jupiter so far. It's been a long ride and we will continue to do so. Don't forget to like, subscribe to our channel to stay tuned with our latest videos and most exciting subjects. Let us know in the comments what you think about these discoveries. We care about what you think.